Good morning. We are talking a little bit today about some basic probability and then building that into a little more in-depth type of issues. So basic probability, we always understand, is our number of successes over our number of total possible outcomes. So when we're looking at some of these things, okay, what's the probability of choosing a girl from the students in our class? So I'm looking around here, I'm like, okay, right now I see 13 of you out there, so that'd be our total number of students. How many girls we got? 1, 2, 3, 4, 5, 9. Ooh, guys, you're outnumbered. All right. So the probability, that's what this P stands for, of getting a girl would be 9, my successes, out of 13. Now, it doesn't mean just being a girl makes you a success and the boys are failures. I'm just wanting to put that out there. Okay. So, deck of cards. Now, I know some of you don't have a lot of experience with cards. So let me help out with a few things here. There's 52 cards in a deck, in a standard deck, which is what we're talking about here. Out of those, they're split up into 26 red cards and 26 black ones, which those are then split up into 13 hearts, 13 diamonds, those are my red ones, over a bit. 13 spades and 13 clubs. Those are my black cards. And then the individual cards from that. Excuse me. So, when I start to look at this, those are the different things that I'm going to have to take into consideration depending on how far the question's asking me to break things down. So, if you're not used to this may take a little getting used to, and I'll probably get it just jotted up on a board somewhere too so you can see it. So when I'm looking at these, I'm like, okay, my first question asks me, what's the probability of getting a red card? Well, there's 52 outcomes every time in the deck of cards, possible outcomes. 26 of them are red. So I got a 1 in 2 shot at getting a red card. The probability of getting a heart, there's 13 of them. Reduce my fraction, I end up with 1/4. And you see how this starts to work. Probability of a red 7. Well, there's diamonds and hearts, so there's 2 different ways I can get a 7, because these cards are in every suit. So a 7 of hearts, a 7 of diamonds means there's 2 chances out of 52, not too great, or 1 out of 26. And then finally, a black heart. You're like, wait a minute, hearts are red. They're not black. You're right. No chance of that happening. Probability of 0. And I go, okay. So most of your classic probability between spinners and cards, and this is our other one, rolling a die, when it asks me to show a sample space, what it's basically asking is, what are the possible outcomes that I could have? So my sample space, when I roll a die, would be, I get 1, 2, 3, 4, 5, or 6, unless some of you have like gaming cubes with 20 sides or something like that. But this is typically what we're going to be talking about. So when I get to the probability of a 4, 1 chance of getting a 4, 6 total chances. Probability of getting an even number, 2, 4, or 6. There's 3 chances, or 1/2. The probability of the number being greater than 1. 1, 2, 3, 4, 5 of those. Nothing reduces though. Or the probability of getting a 7. You're like, Harty, you're messing with us again. Gotta do it. Gotta do it just to make sure that we got things under control. But again, that's more of our basic probability that we're going to be working with. So let's expand it a little bit. Bill, John, Sue, and Bob are all up for a promotion. The boss is going to choose a team of 2 people to lead the department. Everyone's equally as likely to get the position. Show the possible combinations for the team. I like drawing pictures with this, and unfortunately we have 2 people that start with B, or I'd just be using first letters of names here. So Bill could team with John, Sue, or Bob. Now those aren't the only possible teams. So then I go, okay, I already did Bill. Who's next? John's here. Now remember, John already teamed with Bill. John and Bill, Bill and John, same thing. But we haven't paired up John with Sue or Bob yet. Okay, I don't see any repeats so far in the people I have, so I just kind of keep moving down the list. Okay, Sue. Sue's already teamed with John. Sue's already teamed with Bill. Oop, didn't team with Bob yet, though. And then when I get to Bob, well, Bob's already teamed with Sue. Bob's already teamed with John. Bob's already teamed with Bill. So can't do anything else. So there's 6 possibilities here that I'm looking at. 6, 1, 2, 3, 4, 5, 6 teams that I could assemble from this. So the probability that Bill and Sue as a team get the promotion, that only happens in one place. So there's a 1 out of 6 chance of that happening. Probability of the team is made up of 2 men. Bill and John, Bill and Bob, John and Bob. Looks like 3. Bob is one of the people getting the promotion. Team Bob, Team Bob, Team Bob. That's that. Okay, so again, we visually want to look at these things happening. Now, then it starts to get a little crazy here. Okay, a couple is planning on having 4 children. Write out the possible outcomes. Remember, birth order would constitute a different outcome. So like if you have boy, boy, girl, girl, and then the next time it's boy, girl, that's different. Their ages are going to be different for the different children of different sex each time. So when it says write out the possible outcomes, I'm a big fan of making a kind of a tree chart here a little bit, rather than just trying to write it all down. And as you start doing this, you'll be thankful that we're not doing this for like the Duggars or something like that. So, okay. First chance. I can have a boy or a girl. Okay, simple enough. When I go to have my second child, I could have a boy or a girl if I had a boy the first time. I could have a boy or a girl if I had a girl the first time. And this is going to just start to expand. Boy, girl, boy, girl, boy, girl. And you start to see what I mean when I said, luckily we're not doing this for like a family of 10 or 15 or more. Because we're finally down to the end, and even with this is going to get congested. But we're going to get what we needed out of this. So you're like, okay, so what are doing all that to do for me on figuring out the answers? Well, it lets me know how many possible outcomes there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You're like, but Harty, couldn't we have just said there's 2 possibilities, 2 possibilities, 2 possibilities, 2 possibilities, and just multiplied them together and got 16 too? Yes, but that wouldn't have necessarily helped you when you started answering specific questions. If you were just asked for the number of possibilities, I would hope you wouldn't write this out. You would just write 2 times 2 times 2 times 2 and say you were done. Probability of all girls. One way, 4 for 4. Right there. All boys. One way, right there. Otherwise, no. Now, reading into a question is also something that's very critical with these. Probability of at least one boy also could be read as the probability of not all girls. Because, I mean, I could go through here and I'd be like, okay, there's 1, 2, 3. That can get kind of confusing. But if I say, wait a minute, the probability of not all girls, so I'd have 1 minus the chance of getting all girls. So 1 minus 1/16 means there's a 15 out of 16 chance I'm going to get at least one boy. So reading a little deeper into the question can actually save you some time, because maybe you can look at it a little bit different of a way. Okay, something to consider. So then we move up to probability rules here. So the probability of an event is denoted by P sub A. Okay, again, the P stands for probability. Probability of an event occurring is between 0, no chance, and 1, it's going to happen. Can't be over 1, there's not over 100% chance of something occurring. The closer we are to 1, the more likely it is. Okay, the sum of all the different possibilities or probabilities of outcomes in the sample space is 1. So if you know every single option, if you add them up, it's going to equal 1. And then we just got done doing this. The probability of an event not occurring is 1 minus the probability of that actually happening. We just saw an example of that here. So if the probability of an event occurring is 3/5, what's the probability of it not occurring? 1 minus 3/5, or 2/5. Okay? Nothing that's too bad, nothing that's really complex. It's basically just the way it works. So I look and I say, okay, well, so now how are you going to make this more complicated? Because so far, this really hasn't been too bad. Okay, so compound events, multiple things happening. If they're independent, if one doesn't affect the other, if you roll a dice and flip a coin, if I roll a die and get a 3, doesn't mean I'm going to get heads for certain. Okay, so what's the probability you roll a 5? 1 out of 6. Then flip a tail. Heads or tails is 50-50, so 1/2. And I get my probability. Okay, if you roll a pair of dice, again, they're still independent. What's the possibility of rolling a pair of 3s? What's my chance of getting a 3 on the first one? 1 out of 6. What's my chance of getting a 3 on the second one? 1 out of 6. Or 1 out of 36. Okay, the chance of you passing test A is 40%. Okay, let's think a little more on this. Okay, so the chance of me failing A, that would be 60%, because you pass or you fail. They add up to 100. The chance of you passing test B is 20%. Okay. Failing B is 80%. Okay, again, independent of each other. The probability of failing A and B. So when we have it multiple or compound events, we multiply together. Fail A, 60%, but we normally will write these in decimal form. Failing B, it's 80%, or 0.80, and you multiply them together. And again, if you want to put the percentage back in at the end, you can. And so for all 4 of these, because these are the 4 ways that could possibly happen. You fail both, you pass both, or you pass one and fail the other. So we'd go through on each of these. Fail A, pass B, pass A, fail B, and pass A, and pass B. And the reason we did all 4 of these this time wasn't for me to drive you crazy or waste your time, but it was to let you see, okay, here's all 4 possibilities. What do they add up to? 48, 60, 68, 100%, or 1. The probability of all of my events occurring has to add up to 100% or 1. Okay, if I know all of them. But again, in this case, we were talking about independent events, events that are completely, do not affect each other at all. Well, what happens if I have dependent events, where one event does affect another one? Okay, here come the cards again. If you have a deck of cards, what's the probability you will pull 2 aces in a row? Okay, so I have to visualize here. I have a deck of cards. Okay, what's my chances of getting an ace? Well, we know there's 52 cards in the deck. And we talked before about how each of the individual cards, there's 4 of them. There's 1 of each suit. So there's a possibility of getting 4 aces out of the 52. But that's not the question. I want to pull a second one. So we got to visualize. Okay, I pulled the ace of hearts, let's say. So I have that in my hand right now. How many cards are left in the deck with that ace of diamonds, ace of hearts in my hand? There's 51. How many aces are left in the deck with me holding 1 in my hand? There's 3. So I'd multiply straight across and then reduce the fraction down, or hit math enter if you're dealing with one of the calculators in here. And that's where the 1 over 221 is coming from. Okay. Straight across, reduce. Or you can even reduce fractions right away, and that would make it easier, because that goes down to 1/13 and 1/17. So that would be another option for you. But that's how these are going to work. 30 students in class. 17 are boys, 13 are girls. We need a president and a vice president. So order's going to matter. What's the probability of having a female president? 30 students. How many females? 13. And multiply. A female vice president. Now, we just elected a female president. She can't be both. So now there's only 12 females available. And we had 30 students, but we just selected a president. One's gone. So there's 29. And again, straight across. Math, enter, enter, or reduce your fractions right away. That would work too. To get your probability. So now, we've talked about events where they're completely independent, where they're dependent. What happens now if you get events that can kind of simultaneously run or have something that's not exclusive? What do you mean? Okay, from a deck of cards, what's the probability of pulling a red or a 2? Okay, the magic word or means these become plus. Okay, and is times, or is plus. So pulling a red card, I'm like, okay, so a red card, we said before, there's 26 of them, and there's 52 cards in a deck. A 2, there's 4 of those in the deck out of 52. But here's the kicker. So here's what we've actually done. We did the probability of red plus the probability of 2. Is there any overlap? Like, what do you mean? Well, a red card and a 2, are there any red 2s? Well, yeah, there's a 2 of diamonds, there's a 2 of hearts. Okay, right now, if I just add these two guys together, those 2 cards are being counted twice. They're being counted in the red cards, and they're also being counted in the 2s. I can't do that. So I have to minus those 2 cards that they have in common. And what's left over is what my probability is. So if there's something in common, I have to pull that out. And we're going to see that again here in a minute. Rolling a die. What's the probability of rolling a 6, 1 out of 6, or plus a 3, 1 out of 6? Can I roll a 6 and 3 on the same roll? You're like, no, crazy man, you can't. Okay. So I'm subtracting 0 this time. And I'm set. So sometimes you may not have an event that combines the 2 together, but a lot of times we will. Rolling a die, probability of rolling a 6, 1 out of 6, or getting an even, 2, 4, or 6, which is 3 out of 6. But could I roll an even? That's a 6. You're like, Harty, 6 isn't even. You're right. So I have to take that back out. So 4 minus 1 is 3 out of 6, or 1/2. Again, I can't count something twice. So do the individual ones and then minus any that are overlapped. Example 4. In a math class, 14 seniors and 8 juniors. Okay, let's see here. So we've got 14 seniors, 8 juniors. 5 of the seniors are male. So how many of them are female then? Because it doesn't tell us that. Yeah, there'd have to be 9, so it adds up. And 4 of the juniors are female, which tells me there's also 4 males. So when we're doing probability, not only do we need to know the pieces, we need to know the total. So either by adding 14 and 8, or all of my males and females here, I found out I have 22 total students, so that's going to be my denominator. So I look at that and I go, okay, probability of a senior or a male. A senior, there's 14 out of 22. Males, 5 and 4. Oops. Oh boy. 5 and 4. Okay, I got lucky that time. is 9 out of 22. But then remember, we have to subtract senior males. Senior males. You're like, well, what if I forget to? Okay, let's think about that for a second. 14 and 9 is 23 out of 22. We already said you can't have a value greater than 1, and that would be if I didn't have the subtraction. So hopefully that helps remind you too. So 18 of 22, or 9/11. So again, look for that individual piece, minus what they have in common. Okay, junior or female? Junior, 8. Female, 9 and 4 is 13. Junior females. Junior females. And I'm set. You're like, okay. Probability of a junior, 8 out of 22. Or a senior, 14 out of 22. Can you be a junior and senior at the same time? No, Harty, acting like a goof. 22 out of 22, 1. Because you have to be a junior or a senior. You can't be both. That'd be kind of ridiculous. So we're good there. And again, we're going through a lot of different options today because then as the days move forward, we're just going to be doing some slight review instead of throwing a bunch of things at once. I wanted to have everything in one place for you, so that's why we're kind of going in so many different directions here this first day. Okay. My doctor's going over the statistics of a risky operation. 25% failure rate. 75% success because it's going to work or it's not. If the surgery works, there's a 17% chance of infection. 83% chance there's not going to be any though. The surgery can fail and you will still get an infection 3% of the time. 97% of the time, I'm not going to. Those are the types of things I want to look at in questions like this, because then I'm ready for anything. What are your chances of a successful 0.75 and, I'm multiplying, infection-free? 83%, no infection. And again, whether you do that or leave it in its back to its percentage form, I'm good with that too. But notice how I took what information I had and got all of my probabilities situated that way. Now sometimes it may be more straightforward. Example 6. Okay, clothing store. Statistics show if you just buy pants without trying them on, 30% chance being too tight, 10% chance being too loose. What's the probability you find pants that actually fit you? Well, let's see. Too tight, too loose, what's the only other option? Just right. So 1 minus the probability of too loose or tight. Well, I add them together. 30% and 10% is 40%. So there's a 60% chance I'm getting pants that actually fit. I think it's worth the time in that case to actually try them on, but that really has nothing to do with the problem. But you start to see how you can fit bits and pieces of this together. Hey, and one more with our overlap here. To meet state standards, Harlan does some research and discovers 80% of students need help with math, 70% need help with English, and 55% need help with both. Probability of needing help with math or English, okay? Math. 80%, so math is 80% plus English, there's my or, 70%. But again, that would put me over 1. That doesn't make any sense. Oh yeah, minus the people that need math and English because they're already being included in the English and the math groups. So I have to take that part back away. Okay, always be looking whenever there are ors involved. Is there something in common that I can take back out of this? Because if there is, we really need to get that situated. All right, conditional, one of my other favorites. something, I'll be honest with you. I like looking at this in a different way. I understand there's a mathematical formula type way to do a thing, and there's another way. It's called, to me, common sense. I like to use common sense on these, so that's what you're going to get. So I come down here, and I'm like, okay, probability of being independent. Okay, well, let's see. There's 140 total people working here. And how many of them are independent? 17. Okay. That's pretty straightforward. Okay, it's not just one number. Probability is not going to be one number. Probability is going to be a fraction. So don't just write down 17 and think you're done. Probability of a production worker. Okay, there's 92 production workers out of 140. And again, when you're doing these, what you're going to want to do, well, besides the fact you want to reduce, which I didn't do here for a minute, so my apologies on not having that done quicker, is to read into what you're doing. Probability of independent, okay, we got that one, or a production worker. I'm going to leave it with the 140 for now because I like common denominators. But remember, do we have any independent production workers where they go together? Independent production. Ooh, I have 8 of them. I got to take that away. Got to take away the overlap. If you don't, it's not going to work out well. Now here's our last change up. We've dealt with and, we've dealt with or. Now a new word gets introduced, given. Okay, we're narrowing our group down that we're looking at the probability for. So when you're doing these, whatever comes after given is what your total possible outcomes are. So how many Republicans are there? There's 55. That's the group I'm working with now. I'm not grouping with the total with anymore. I'm being told it's Republicans. So this is the only place I'm working with now. Okay, which Republicans am I working with? The Republicans that are executives. Okay, so you see where I'm heading here? Here's the group you're working with. Okay, so within this group, how many of them are in here? Nice thing with givens, we don't have to deal with all the ands and ors and all the other things like that. So again, here, independent, given a production worker. Okay, production workers, 92. That's the group I'm being given. Okay, so within the group production workers, how many of them are independent? 8 independent production workers. Okay, so you've got to look for keywords. And is multiply, or is add. Given means I'm narrowing down my focus group. You're like, okay, I kind of see what you're saying. Now we get to play a little bit, and then we're going to be situated here. Okay, make a tree showing the possible outcomes for flipping a coin, then rolling a die. Okay, well, flipping a coin, I can get heads or tails. And then if I roll a die, I could get heads in 1, heads in 2, heads in 3, heads in 4. You get my idea. Heads in 6. That basically is just telling me there's 12 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 when that happens. So my denominator on every problem dealing with those in probability would be over 12. Okay? Just letting you see how you can visually do this. Okay, nothing else to do with it here, it's just letting you see it. So we finally make it to the back. We're like, okay, class of 30 students, I got to choose a president, a vice president, and a secretary. Student can only hold one position. How many outcomes are possible? Okay, again, I am visual. I want a president, I want a vice president, I want a secretary. Once you take one office, you can't have another one. This is not a dictatorship. Looks like we're dealing with a democracy here. How many choices do I have for president? There's 30 students. Okay. But now I've picked my president. Comes time to pick the vice president. How many options do I have left? Now there's only 29 because the president can't be the vice president. And you see the idea here as we get down to secretary. Take one away, take one away, take one away. and multiply them together. This is called, not only with your counting principle, but you also can run into a permutation because order of the people matter with a president, vice president, and a secretary. We're getting to that here momentarily. Okay, revisit the 4 children problem. Create a tree diagram showing the possible outcomes. We already did that. That was so good of us to do ahead of time. How many combinations were there? We counted them. There were 16. And that kind of lets you see where 2 times 2 times 2 times 2, there was 2 options each time. Got us to the same thing. Excuse me. So that let us see how many possible combinations there were. And finally, and then we'll tone way back on the notes here, moving back into the days ahead. Permutations and combinations, which is going to be the focus of your homework tonight. Okay, permutations, order matters. Picking a president, a vice president, a secretary. Okay, you're having a contest, picking first place, second place, third place. Order matters. We do what's called a permutation. Combinations is where order doesn't matter. The toppings on your pizza, whether you say it's sausage, green peppers, and onions, or green peppers, sausage, and onions, it's the same stuff on your pizza. Or I'm picking a committee of people in general to look into something. Nobody has a specific job, it's just a committee. Order doesn't matter. So here we have 32 people in class. You're choosing a team, generic, of 3 people. How many possible ways can you choose them? Okay. Order doesn't matter, it's just a general team. Now instead of having to do something fancy, we let the calculator work for us. So here's how this is going to work. We want to find out how many different 3-person teams we can make. So we're going to do 3. No, we're not. We're going to do 32 because that's how many people we have to choose from. The calculator can do this for us. So I'm going to hit math. I'm going to arrow all the way over to PRB, stands for probability. You'll notice numbers 2 and 3, these are the 2 we're going to be dealing with. If it's a permutation, we work with 2. If it's a combination, we work with 3. We're dealing with a combination, so we hit that. And then we hit how many we want to choose. And it gives me the answer. Now, some of you may be saying, well, wait a minute. Couldn't I do this like I did example 2 up above? Couldn't I just do 32 times 31 times 30? Ooh. Why is the answer different? Again, down here the order doesn't matter. So if I have Joe, Susie, and Paul on a team, or Susie, Joe, and Paul, or Paul, Joe, and Susie, see, those are the same 3 people over and over and over again. They all get counted in those different ways when we do it this way, but the order doesn't matter here. You're going to have fewer options when the order doesn't matter. So that's why I've got to do it this way instead of using the fundamental counting principle. Okay, how many ways can 8 students be placed in a line? Ooh, if we're in line for like Black Friday, ooh, if we're here for chicken bowls. Does it matter if you're in the front of the line or the back? Yes. So, I have 8. I'm going to be picking 8. So again, number of options, math, over to probability. This time it's a permutation because the order matters. And I am placing everyone. And I'm set. So again, as I'm doing these, how many ways can a group choose a committee, general, of 4 boys and 4 girls if there are 20 boys and 15 girls to choose from? Okay. Now this time, there's an extra little something working in here, and here's what I mean. Not only do I have a generic committee, but I have 2 separate things going on here. So a committee of 4 boys, okay, but how many boys are there to pick from? Well, there's 20. Okay, well then I have another part of my committee because I want 4 girls, and there's 15 to pick from. So now I've got to go, okay, so when I'm doing this particular problem, so we're going to go ahead and multiply these two combination possibilities together. You're like, holy cow, man. Glad you don't have to make a chart for that, right? Holy moly. So again, that gets kind of large here. And finally, and this one gets argued every time, how many ways can I arrange my videos and DVDs on my shelf? I have 5 videos and 7 DVDs. All the videos are together and all the DVDs are together. What I always tell people when they see a problem like this is think about the library and library books. Does it matter which order the library books are on the shelf? Sure. They're there, but the order matters for where you locate them, where you find them. So here, we're going to be looking at a permutation. And it's also important that they tell us they're together. So if my videos are together and I have 5 of them, I'm putting those 5 together in their order. If my DVDs are together, I got 7, I'm putting them together in their order. So one more time here. Permutations, again, because our order is going to make a difference. Okay, and your job with this is to work on practice 82, 83. We will start working on counting principle and some more things with odds tomorrow, but this was just kind of a general overview. Most of your homework is going to be from this last section, kind of dealing with permutations and combinations. And like I said, we'll deal with more tomorrow.